everyone, and sorry for changing the lecture time today. So for those of you who will be watching the video afterwards, please feel free to ask me any questions that you have by email. So you can just send me an email at my last name at cse.ust.hk. Okay, so let me share my screen and start the current lecture. Okay. So we talked about proof of stake last time, and this time we're going to go into more detail, and we're going to actually talk about a very specific type of proof of stake. It's called Uroboros. But before that, let me just review what we saw in the last session. So we saw the basic idea of proof of stake, that the miner is going to be chosen randomly, and the probability that a particular person gets chosen is proportional to their stake. So another way of thinking about this is that we can consider all the coins or all the units of currency that exist on our blockchain, and then we can say that we randomly choose one of them with uniform probability. And then the owner of that chosen coin gets to be the next miner. Okay? So if we do such a thing, we have to use the smallest possible unit of currency. So for example, if I wanted to somehow change the Bitcoin protocol so that it becomes a proof of stake protocol, I have to have a way of randomly choosing one Satoshi of all the money that exists on the blockchain. Or on the Ethereum blockchain, I have to randomly choose one Wei, so the smallest possible unit of currency. And after we choose that random coin, of course, we can say whoever owns this coin has the privilege of adding the next block. Now, we talked about several problems that this can have. So one problem that we have is that the stakes change rapidly. So every time that you make a transaction on the blockchain, you're sending money from yourself to someone else. And so these probabilities have to change with every transaction, and that's just too much change. It's not really stable. We talked about this idea of having snapshots to solve this. Now, we had a problem about reaching consensus about who the next miner is. So this was the idea that suppose I have n blocks, and I want to somehow choose who's going to mine the next block, the block number n+1. And here the problem was that, first of all, we want that person to be chosen randomly in proportion to their stake. But at the same time, we want everyone to reach consensus, because everyone in the network should be able to verify that this person really had the right to add the next block, that this person was really chosen to add the next block. So this is the problem that is going to take most of the remainder of this course, and we're going to talk about it a lot. Another problem we saw was this idea that we can have a lot of forks, because now we said that if I'm chosen to add block n+1, I was chosen based on proof of stake, I was chosen randomly, so I don't have to prove anything other than the fact that I'm chosen. Right, so I don't have to do a proof of work. I don't have to really solve the puzzle. It's just that if I'm chosen to be the miner of block n+1, then I have to create a block. I have to sign that block so that it's verified that it's really coming from the miner who was chosen. And then I can just publish that block. But now the problem is that I can freely create as many of these blocks as I like. So if I'm a malicious miner here, for example, I can create 3 different blocks and sign all of them. And then we also talked about this idea that if we don't set the incentives right, then the next guy who's going to add block n+2 is going to also have to follow my lead and extend all of these chains, because this person has no way of knowing which one of these chains will become the longest chain, and they don't want to lose on their transaction fees and any other fees that are paid to the miners. So they would just do the same thing. And the idea that we had here was that we can solve this one actually pretty easily, and this was the idea of disincentivizing forks. So what do I mean by disincentivizing them? I mean that we can allow each person to show that the previous miners have cheated. So we can let miner of block n+2 to add some specific transactions to his block that says, by the way, miner of block n+1 has cheated. Here are two different blocks that this miner has signed. So this is proof that this miner has cheated. And then we can talk about incentives here. We can say that if a miner cheats, they lose, for example, all of their transaction fees that they obtained here. And then we can also have an incentive for people to report the cheating. So we can say that if miner n+2 reported that miner n+1 has cheated, then maybe he gets half of all the fees that were belonging to miner n+1 before. So we can have these ideas that make it very much irrational to create forks like this. And so one last problem that we had was this problem of having non-cooperative miners. So suppose that you are just a normal user on a blockchain. Most users don't really understand how the blockchain works. They just bought some coins using an exchange, and they're not really doing any kind of mining or so. So it might be the case that someone gets chosen to mine the next block, but they're not really cooperating in the mining. And we somehow need to make sure that our progress is not impeded by that. We have to make sure that the blockchain can go on even if some people do not take part in the mining. Okay, so today I'm going to talk about a very specific proof of work protocol, and this was actually the first proof of stake protocol, and this was actually the first proof of stake protocol that was shown to be secure. So it has formal proofs of different security properties. I'm not going to be very formal about this because the proofs actually need a lot of martingale theory, which is a subject I love, but I cannot teach at undergraduate level. So let's go and talk about this. So the protocol we want to talk about is called Uroboros. And Uroboros, if you just Google this, is actually the name of a very old Greek icon, which is like a snake that is eating its own tail. And we will soon see why the name is like that. It's actually because, in a sense, each block, or actually each epoch of blocks, creates the randomness for the next set of blocks. Okay. So what are the ideas in Uroboros and what are the assumptions? So let me start with some of the assumptions that we have in Uroboros. And this is by no means a complete list. I'm just going to list the ones that we're actually going to use in the course. So one assumption that we have is that, well, as usual, we want to have this assumption that at least 50% of the blocks are mined by honest miners. Okay, so in proof of work in Bitcoin, what this assumption translated to was that I want to make sure that at least 50% of the hash rate belongs to honest miners. But here what I want to say is that I want to say that more than 50% of the stake belongs to honest miners. Okay. Now, if I want to add this assumption, I have to first talk about what I mean by an honest miner. So we can give different definitions, but the definition that I want to work with for honesty. So who's an honest miner? Well, I want an honest miner to first of all be cooperative. So An honest miner is someone who, if chosen to create a block, will actually create a block. Okay, so I would not accept non-cooperative miners or people who just don't care about mining as honest. Honest, by my definition, means that if you're chosen to add a new block, you will add a new block. But another thing that I'm assuming in honesty is that an honest miner will not create a fork. So an honest miner who's asked to create some block, for example, block n+1, will not create several different copies of it, and will not create forks like this and sign all of them. And when I'm saying this, I'm also assuming that this is irrespective of the state of the blockchain. So even if block n+1 was already forked, and you're an honest miner and you want to create block n+2, you will only create one block n+2. So you will not add all three. That's the definition that I have for honest. And again, as I said here, we can incentivize miners to be honest. So that's not a problem generally. So it's not like honest miners are irrational. But here, I don't want to really talk about incentives. I just want to talk about assumptions that we have, and I want to use those assumptions to prove that we can have a working ledger, a working blockchain. So my first assumption is that 50% of the stake, at least, actually strictly more than 50% of the stake, belongs to honest miners. And so honest means cooperative. So they actually, and what I mean by cooperative is that they actually create new blocks when it's their turn to do it, and also non-forking. Okay, so this is the first assumption that we have. Now, the second assumption that I want to make here is an assumption of synchrony. So I want to say that the network is synchronous. Now, what does this mean? This basically means, in simple terms, that everyone on the network has a clock, and the times are kind of the same. I mean, they might be a little bit off from each other. So, for example, everyone is using just the clock on their computer, and they're all using the Unix time. And so the time that they have is almost the same, maybe not exactly. But not only that, but also if someone sends a message on the network, it will be delivered to everyone. And it will be delivered within a specific amount of time. So the messages are going to be propagated in the same way as in Bitcoin or as in Ethereum. So we're going to have this gossip protocol that we talked about before. So basically the idea is that each node connects to a bunch of other nodes, and whenever they see a message, they just send it to all of their neighbors, and then the neighbors also send to all of their neighbors, and so on. So the message will very soon reach everyone in the network. But now we're going to also have an assumption that this process will take a finite time, and we're going to put a bound on it. So, for example, I can say that it takes at most 20 seconds to deliver all the messages. So if you send a message now, you can be sure that everyone on the network sees your message within the next 20 seconds. Okay? So these are some of the assumptions that we have. And now I want to define how the blockchain works. So this is how our blockchain will work. So the blockchain. So we define something called a time slot. Okay, so a time slot is basically just our unit of time on this blockchain. And We generally define it by just its starting time and end time. And usually all the slots have the same amount of time. So it's just like a period of time of fixed length. And actually, in most implementations, this fixed length is maybe 20 seconds. But we don't really talk about what the exact time is. I just want to talk about this. I want to talk about the whole protocol based on this abstract notion of a time slot. Okay, now what I want to do is that I want to say at every time slot, there is one person or one miner who has the privilege of adding new blocks. Okay? So, but I also have a fixed starting block. So let's say, let me actually first say this one. So I have a fixed starting block, or a fixed genesis block, sometimes they call it. So this is the very first block in my blockchain. So that one's fixed. And then after that, in every time slot, in every 20-second time period, there is exactly one person who's allowed to add a new block. Okay? So at every time slot, only one person or one miner is allowed to add a block. Okay, so if you want to think about this, so we have several time slots. Let's say I start from time slot 0. So I'm going to write T here for time. Then I will have time slot 1, time slot 2, 3, 4, and so on. And at time slot 0, I have my starting block or my genesis block, which is something that is fixed. And then I have a unique miner at every time slot, who's the person who can actually add the block. So I call it M1 here, M2, M3, M4. So these are identities, these are public keys. Now, how does it work? Well, we start with the genesis block, and then while we're in the first time slot, miner M1 can choose to add a block. And if they want to add a block, the way they do it is that they simply announce the new block to the whole network. And this block should also have a signature from M1. So no one else can create a block because everyone knows that we are now in this time slot. And if we are in this time slot, everyone knows that this particular miner can do the mining only. So everyone expects a signature from this particular miner. So we have to somehow connect this notion of synchrony that we had with our notion of time slots. So the way I define synchrony now is that any message that you send in any time slot will be delivered to everyone else in the network by the end of that time slot. Okay? So the idea is that if miner M1 creates a block at time slot 1, and announces it, then by the end of time slot 1, everyone in the network would have seen it. Okay, so now what happens? How can I create a blockchain? So let's say that at time 1, M1 is an honest miner, and they create one new block. Now, just as in the Bitcoin blockchain, they have to say where the previous block is. So it will have a pointer to the previous block. But it will also have the time slot in it. So this block would say that I'm a block, I was mined in time slot 1, I was mined by this person, here's a signature, here's a list of transactions, and here's a pointer to the previous block. Okay? So things are very similar to Bitcoin. The only difference is that instead of just having a pointer to the previous block, we now also have this notion of time slot. And instead of having a proof of work witness, a nonce that makes the hash small, now we just have a signature by the miner who was chosen to mine in this block. Okay, now let's go on. Let's say that miner M2 is not cooperating. Maybe this is someone who wasn't interested in mining. So in time slot 2, no new blocks are created at all. So then when time slot 2 ends, no one has received a new block. So everyone knows that, okay, this wasn't a cooperative miner. No new block was created. So we just allow that. That's fine. Then when we get to time slot 3, maybe again miner 3 is now a cooperating miner, an honest miner. So this miner creates a new block. Okay, so creates this new block, signs it, and of course the block should also have a pointer to the previous block. And now you see this weird thing that we only have in proof of stake and we didn't have in proof of work. So we have two different concepts here. We have the concept of our time slot, and this block was created at time slot 3 by the miner who was allowed to create a block at time 3. But we will also have another concept, which we can call depths or lengths of the chain. And this is different, right? Because no one created anything here. So I can say that the length of the chain was 0 here, the length of the chain was 1 here, but here the length of the chain becomes 2, right? So we're at time 3, but I have 2 pointers that I can take to get to the genesis block, so the length of this chain is 2. Okay. Now let's say that again 20 seconds passes, so we are now in time slot 4. And we have this M4, and suppose that M4 is a malicious miner. So as a malicious miner, what he does is that he creates 2 different blocks. Okay? And he creates these 2 different blocks and makes them point maybe to the same previous block. So both of these blocks say that our previous block is this one. Both of them have a signature by M4, and both of them say that we were created in time slot 4. Now, this is of course a fork. So the problem that everyone on the network now has to deal with is, okay, we have a fork, which chain is the consensus chain? And again, the rule that we use is very much similar to Bitcoin. So the rule that we will have is that the longest chain is the consensus chain. Okay. Now, but the problem that we have here is that, of course, the longest chain is not unique because this guy forked it. So both of these chains have a length of 3. So what happens if we go on? So let's say I go to time 5 and I have miner M5. So now this is the part where I'm going to actually use my assumption that at least 50% of the stake belongs to honest miners. So miner M5 was chosen at random. So with a good probability, with probability more than 50%, M5 is honest. So if M5 is honest, then they're not going to extend both of these chains. Because they're honest, they're going to extend at most one of these 2 chains, even if they have seen both of them. So at this point, M5 just chooses one of these 2. So creates a new block, and maybe chooses this one. Okay. And now this is a block that has length 4, and it's the only block that has length 4. So this is the consensus chain. And of course, M5, as soon as they add this block, they will also announce it to the whole network. So by the end of time slot 5, the whole network has heard about this block. And since this is the only block that has length 4, everyone in the network now agrees that this is the consensus chain. And so in this case, in this very simple example, the forking here has failed, right? So M4 tried to fork, but because the next miner was honest, the next miner basically defeated M4's fork and again made everything unique. Now, as I said before, we have to talk about incentives. Like, why should the next miner actually do this? In Uroboros, we're just assuming that more than 50% of the stake are honest, belongs to honest miners. So I can say that with probability more than 50%, this guy is honest, and they're not going to create more than one block. But in practice, actually, the way that we do this is what I talked about at the beginning of this session. And the idea is that M5 can include the 2 different blocks that existed at time 4. And they can say, hey, look, the miner for time 4 cheated. And here's the proof. Here are the hashes of 2 blocks at time 4 that were both signed, that they're different hashes, so they were different blocks, but they were both signed by M4. And here's the signature. So this proves to everyone on the network that M4 was cheating. And then we can add some incentives. We can say that, okay, if M4 is cheating, we're going to take away all of his transaction fees or mining fees that he earned here. And we're going to give maybe half of it to M5 so that we also incentivize people to report the cheating. Okay? Now, so this is the way that we want to make sure that in the long term, the chain would become unique. So we want to have a property similar to the property that we have at Bitcoin, that if you have some block, and if you have, let's say, 6 confirmations, if you have 6 blocks after this, then we want it to be very unlikely for this block to be forked out and basically removed from the consensus chain. Of course, 6 is a number that we used in Bitcoin. Here, we will probably change our number based on how much time we're allowing for each time slot. Okay, but this was the general idea. And I'm going to show you some more examples of what can go wrong. There is actually a proof in the Uroboros paper that this general idea works. So as long as you assume that more than 50% of the stake belongs to honest miners, and as long as you assume that honest miners will only add 1 block when it's their time to add a block, this will ensure that we will have a working blockchain. Okay. But here's the thing. I actually didn't talk about a very important detail here. And the very important detail was how the miners themselves are chosen, right? So I just assumed that at any given time I, we have a miner MI, and I just assumed that everyone on the network agrees who's going to be this miner. So now we have to go back and fill in that very important detail. Okay. Now, the way we do this, actually, the way we choose the miners is using a concept called an epoch. Okay. So, formally speaking, an epoch is just a sequence of, let's say, R consecutive slots. Okay, so let's again talk about our time slots. We have time 0 where we had the genesis block. We have time 1, time 2, and so on. And now the idea is that I want to take the first R of these. So I want to take all the slots from time 1 to time R, and I want to call this epoch number 1. Then I will take all the slots from R plus 1 to 2R, and I call this epoch number 2, and so on. Okay, so now instead of just thinking about time slots, I'm thinking about time slots and also a grouping of the time slots into consecutive sets of size R. Okay, so this is 3 and goes. Now, as we talked about this before, at each one of these times, I can have one or several blocks, and this is the situation that we had here, and each block also has a pointer to the previous block, which also defines the length of the blockchain up until that point, and we said that the length is not necessarily the same as the time. But the thing that I want to focus on is how to choose the miners. So at time 1, I need to know a miner M1, who's going to be the person who can add a block at time 1. At time 2, I need a miner M2, and so on, and here I will need MR. And then MR plus 1 to M2R, and M2R plus 1 to M3. Okay, now here's the idea. We say that every epoch is responsible for generating the miners of the next epoch. Okay, so during epoch E1, or maybe most likely at the end of epoch E1, what I'm going to do is that I'm going to generate R random numbers, and these R random numbers are going to tell me who the miners of the next blocks are going to be. So in block E1, maybe just at the end of it, or actually I can do it at any time during E1, but anyway. So in block E1, I generate these numbers. I generate MR plus 1 to M2R. And in epoch E2, I generate these numbers. Okay, and so on. And of course, my initial block, my genesis block, gives me the random numbers that I'm going to start with. Of course, the initial ones are not really random because they're just going to be created based on the genesis block. So in my first epoch, these numbers are not really random, but what I want to say is that I want to say in E1, I'm going to actually generate random numbers. And then these random numbers will tell me who the miners are going to be in E2 and so on. And now you see why it's called Uroboros, because in a sense, each one of these epochs is creating the randomness for the next one. So you can see the idea of like a snake eating its own tail. But now we have kind of a harder problem in a sense. And the harder problem that we have is how do you generate randomness? And how do you generate it in a provable manner? So I just want to say one more point here. And so when I say we generate randomness in E1, we can do it in many different ways. Usually what we do is that we say that the miners that were chosen in this epoch can also take part in generating the random numbers for the next epoch. But we can also have a separate group of people who are chosen in E1 to just create the randomness for E2. So I'm going to assume that it's the miners who are also generating the randomness for the next epoch. but this is not necessarily a requirement. So you can have another set of people do it. Now, okay, so here's our problem. So let's call it the RNG problem, or the random number generation problem. Now, this is the problem that I have. I want to say in epoch EI, generate random numbers, and these random numbers are going to be the miners that are going to be used in the next epoch. So I'm going to say generate exactly R random numbers, that will define miners in the next epoch. We also need the epochs because of this problem that we had here, that the stakes change. So in epoch E1, I'm going to generate some random numbers, and these numbers are going to point to coins. So if I have a bunch of random numbers, what I know is that the owners of these coins are the ones who get to create the next blocks, are the ones who are going to be able to mine in the next epoch. But when I say the owners, that's not very well defined, right? Because we're doing transitions and the owners are changing. So I can just make it well defined by saying that the owners at the beginning of E1, or maybe the owners at the end of E1. You just have to make the right choice, and you have to make it well defined. So you have to make it so that when you generate some random number, you can uniquely say, okay, now that this random number is generated in this epoch, what does it mean? Who's the miner who gets to actually mine in the next epoch? Okay, and for that we need to have some snapshot of the stakes, and we have to say that, okay, we're generating random numbers, and then we're saying at this particular time, whoever owned the coin with this random number is going to be our miner. Okay, but that part is, again, just mostly implementation detail. I'm not going to talk too much about it, but this is now our problem. So in each epoch, I want to generate R random numbers, and these are going to give me the miners in the next epoch. Now, what properties do I need? So what are my security requirements? Or actually, maybe just requirements, not all of them are about security. But anyway, so what are my requirements for this random number generation? So let's say that these are random numbers. Let's just give them some name. Let's call it R1, R2, because random number 1, random number 2 to RR. And okay, I also have a bound for them, right? So all of these are going to be in the set 0 to some n-1, where n is the number of coins that I have in my system. Okay, so this is exactly what I want to generate. And now what are my requirements? Based on this, I can say that, well, first of all, I want them to be generated uniformly at random. Okay, so I need uniform generation. What does this mean? This means that each one of the RIs should be sampled according to the uniform distribution over 0 to n-1. So for each one of the RIs, I want that RI to be chosen really truly at random and with the same probability between the numbers from 0 to n-1. Of course, I also need independence. or actually I would even say I need pairwise independence or so on. Basically, what I want here is that I want every Ri to be independent of the rest. Okay, so Ri is independent of the set Rj, j not equal to I. Okay. So this is again a very natural thing because I want to generate different random numbers and I don't want there to be any dependence between them. So I want them to be uniformly generated and I want them to be independently generated. But what else do I need? Well, I also need to reach consensus, right? And what I mean by this is that I want to make sure that by the end of my epoch, so by the end of my epoch, what was my epoch called? Okay, I called it EI, maybe I is not a good index there, let's call it EK. So I want to say by the end of EK, all honest nodes reach a consensus about all RIs. So I say all honest nodes, and what I mean by that is all the nodes of the network that are actually following the protocol. So if I have a dishonest node on the network, I don't care what the dishonest node thinks, because a dishonest node can always say, oh, I don't agree with this. I don't care. What I actually care is that I want to make sure that all the honest nodes agree about the value of the RIs. But now I also need unpredictability. So what does unpredictability mean? It means that no one should be able to guess beforehand what the values are going to be. Okay? Because it's actually pretty easy to create this randomness. For example, I don't know, using the hash of the blockchain or using the hash of one of the blocks or some idea like that. But it would be predictable. So I want there to be a very well-defined separation between the time where no one knows what the random numbers are going to be and the time where everyone knows. Okay, and finally, I want to have a system that is tamper-proof. What does tamper-proof mean? It means that no one or no group of people should be able to change the result of the randomness. Okay? So this is actually very similar to some of the topics that we have talked about before. We've talked, for example, about how we can do a lottery. Right. We have recently in our homeworks had a homework about doing rock, paper, scissors and a homework about doing auctions. Right. And many of the ideas that we had there are going to also appear here. And I don't need to tell you that it's not fine to just use the block hash or the hash of a series of blocks or anything like that, because of course they're not tamper-proof. If you use anything that is based on the hashes of the blocks, then the miners can tamper with it. Actually, let's see an example of this. So I'm going to call this a naive example. So let's say that R is 1. So every epoch has exactly one time slot in it. And let's say that the miner for each block is chosen based on the hash of the previous block. Okay. So let's say that in this naive example, I have my first block, or block 0 actually, which is the genesis block. And then I take, okay, so let me call this actually, okay, let me call this B0, block 0. And then I want to choose a miner for each block. So B0 doesn't need a miner because it's just how we start our blockchain, and we can make everyone agree about what's going to be in B0. But then I get the hash of B0, and I take that modulo n, and I say this is the miner for B1. Now this person gets to add B1, and then as soon as they add B1, I can take the hash of B1 modulo n, and say that this is the miner who gets to add the next block. So this miner adds B2. And then I again do the same thing. Just take hash of B2 modulo n and say that this is the miner of the next block. Now, why is this a terrible idea? It's a terrible idea because just consider an attacker that has maybe 10% of the stake. Okay, so let's say I'm an attacker, I own 10% of all the coins, so I should be able to, on average, mine 10% of the blocks. And let's assume that everyone else on the network is honest, so I'm the only attacker. Now what happens? So I wait a while, and since I have 10% chance of being chosen each time, at some point, eventually I will be chosen. So at some point, this miner here would be the attacker. So let's say this is for block BI. Now, as the attacker, I'm the one who gets to create this block, right? And the only thing that I need to mine this block is my signature, because I'm the designated miner for this block, so everyone just checks that the block that was announced has the right signature. But I'm the one who forms this block. So I can just form different blocks and experiment with their hashes. I form a block, I compute its hash to see if I will become the miner for the next block. And if I don't, I will just not publish this block. I will discard it, create another block, maybe with some random transactions in it or some extra random nonsense so that the hash changes. And then again, I look at the hash to see if I'm going to be the next miner. And if not, I will ignore it. And I will continue this until eventually I find a block where if I add that block, the hash of that block modulo n would again make me the miner. So then I will add that block. So I've added block BI, and now for block BI plus 1, again, the same attacker, or me. Okay, so for block BI plus 1, again, I'm the one who gets to mine it. So now I can mine block BI plus 1. Again, I do the same attack. So you see, even though I have only 10% of the stake, I can make sure that I mine every block from here onwards. And this is like a very classical example of why you should not use block hashes. And we've seen many other examples of things going wrong in proof of work and in smart contracts when you use block hashes. But here you see that in proof of stake, we have a similar situation. You should not depend on the hash of the block. Okay. So one nice question in the chat is that, wouldn't it take a long time to reverse engineer the block hash like this? Actually, it depends on your on your stake, right? So if you have 10% of the stake, on average, you just need to choose 10 different blocks until you find the block that gives you the right to mine the next block. But in a sense, this attack is like doing proof of work, right? So the attacker is doing a proof of work of trying to create a block that would give themselves the right to add the next block as well. But the difference is that this is like a trivial proof of work, especially if you have a big enough stake. If you have like a stake of 10% or even 1%, then you just need to choose maybe 100 different nonces. And yes, we will have enough time for that because, well, it's because of the length of our time slot. You see, I'm assuming synchrony, so I want to have my time slot large enough that I can be sure that everyone in the whole world on the network would hear about everything that is happening on the blockchain within the same time slot. So I have to make my time slot quite large, maybe at least 10 seconds. But normally we would say 20 seconds. And 20 seconds is more than enough time to do these kinds of things. Like this will take less than a millisecond. Okay, so back to our random number generation problem. So we just saw that we cannot use block hashes. So what else can we do? Now we can go back to the ideas that we had for lottery and to the ideas that we also had for playing rock, paper, scissors and for playing an auction, homeworks 4 and 5. And that's the idea of using a commitment scheme. Okay, so the idea was simple. We wanted to say that if we have a bunch of players and they want to come up with a random number all together, what we can do is that we can ask each one of them to give us a random number, and then we can take the XOR of these random numbers and say that this is our final random number, right? But as we've seen before, we cannot just do it like that, because if I do something like that, and if I have, let's say, 5 different players, one of them, who's the attacker, can just wait for the other 4 to announce their numbers, and then he can announce a number that makes him the next miner or makes him win the lottery or whatever use case we have for our random number generation. So instead, we saw that we can use a commitment scheme. And a commitment scheme is that they first announce the hashes of their choices. Of course, they have to also choose a nonce. And then after everyone has chosen their, after everyone has committed to their hashes, then everyone reveals their choices and their nonces. But okay, in this commitment scheme, so let's say that I'm in epoch 2 and I want to generate random numbers for finding out who the miners are going to be in epoch 3. Okay? So who are the people who are going to take part in generating this random number? As I said before, a very natural choice is to just say, okay, if you are a miner in E2, you get to take part in generating the random numbers for the next epoch, for E3. Another way is to just have 2 sets of miners, one set of miners who's only interested in creating blocks, and another set of miners who's only interested in creating randomness. And then we can say, okay, the randomness miners will do this. But for now, let's just keep things easy, and let's say that these miners are going to take part in a game, and this game is going to give us the random numbers that we will have to use for the next epoch that will tell us who the miners are going to be in the next epoch. Okay, so we start like this. Let's say that suppose the miners in the current epoch are, let's call them M1 to MR. So these miners play a game. Okay, and here's the game that they will play. So I'm specifying my protocol in step 1. So just going back here, I need to generate odd random numbers, but I'm just going to tell you how to generate one random number, okay? Because we can just do this in parallel r times, and then we will have r random numbers. So let's just assume that I want to generate a single random number. It's easier. Okay, so in step 1, each one of our players, each player MR chooses 2 numbers. So what are the 2 numbers? Each player MI chooses 2 numbers. So one is the number that is actually going to be used in the game, and the other one is a nonce. So let's give them some names. So let's say they're XI and NI. So XI is the actual number that we want to use, and NI is the nonce of player MI. Well, actually, okay. And so in step 2, well, we can also assume that all of these XIs and NIs are basically between 0 and n-1. So we are generating numbers that are between 0 and the number of coins. So in step 2, this MI, the miner, announces the hash of XI put together with NI. Okay, and let's say that this hash is called HI, the ICE hash. So this is very similar to all the commitment schemes that we have seen until this point. Now, after everyone announces, so we wait for everyone to announce. Then the next step, step 3, is that each miner MI actually reveals their choices and nonces. So they reveal XI and NI. And then in step 4, everyone on the network can just take the XOR of all of the XIs. So everyone would just say our random number is equal to the XOR of all the XIs. Okay? And so now we have a random number that we can use. Now we have to talk about a lot of details here. Okay, let me just answer some questions in the chat. So one question is, what if all miners in an epoch end up being uncooperative? Who would generate the random numbers for the next epoch in this case? So this is a very unlikely case, and we assume that it just never happens. So here's the thing. If all the miners in this epoch are non-cooperative, that means that all the miners in this epoch are dishonest, because remember that when we were talking about honesty, the assumption was that they will cooperate, they will take part in the protocol. And we said that at least half of all the mining power, at least half of the stake, belongs to honest miners. So the probability that all of these people here are uncooperative is less than 2 to the power of minus r. And if we choose r to be large enough, if we say that our epochs are large enough, for example, if I say my epoch is 100 blocks or 1,000 blocks, or okay, I have to say slots, 1,000 slots, then the probability that no one in this epoch is cooperative, or actually no one in this block is honest, is less than 2 to the power of minus 1,000, which is effectively so small that we don't care about it in the real world. But we can also have fallback mechanisms. So we can have like some situations where we say, okay, if all of them were non-cooperative, then at this particular case, we will just take the hash of the previous one. So, and if we do that, then the next epoch would not be truly random, because we're just using the hash and it's people can tamper with that. But then after that, the next one will again likely be very much random. So again, these are very low probability events, and it's like the probability that some asteroid hits the Earth and we all die is much higher than the probability that everyone in the epoch is non-cooperative. So in practice, we don't really care about it. Okay, so there is another question here. What if someone don't reveal the random number? I'm going to get to this. This is actually at the core of why we cannot just use commitment schemes. Okay, now let's see what happens here. Well, first of all, I have to fill in some details. So what does it mean when we say we wait for everyone to announce the HIs? Well, this means that we just wait for one slot, or we wait for 2 slots. 2 is definitely enough. 1 would also work. And why is it that we don't have to wait any more than this? Because we assume synchrony. We assume that everyone, whenever they announce anything on the network, it will reach everyone else within 1 slot. So if we wait for a number of slots, we can be sure that if someone actually announced their hash, then their hash would have reached everyone else and everyone would agree on it. Okay, so that's the first thing. What else? So another thing is that when I talk about announcing, this announcing always comes with a signature, right? So when I say MI, this player announces this hash, we have to have a way to verify that the hash actually came from this player. And the way that we do that is that the announcement should also contain a signature. Now, another problem is what happens if someone is malicious and they announce several different hashes. So in that case, we can again go back to this idea here of disincentivizing these kinds of things and actually punishing them. So we can have some fees, right? Normally, when someone adds a new block, they get a block fee and they get transaction fees. So similarly, we can give some fees to the miners for taking part in the random number generation. And what we can say here is that if someone cheats, they will not get their fee. They will not get, so if they announce several hashes, more than 1 hash, they will not get a fee. If they announce no hashes, they will not get a fee. And so on. So this punishes people who want to cheat. And again, we can have a system similar to before that we also reward people who report someone else's cheating. But that's not such a hard problem. Okay. Now, because we have this kind of commitment scheme, by the end of step 2, everyone has committed to their hashes, right? So in step 3, okay, so this is very similar to how we played rock, paper, scissors, right? So in rock, paper, scissors, people had to commit to their choice before knowing the choice of the other people. And this is also similar. Each player is committing to their choice, to their number xi, before knowing what the other players are playing. So in a sense, it's as if we are simulating a one-shot game where they're playing at the same time. But now we have this problem of revelations, where after everyone has announced their hashes, now we have to reveal. Now, we cannot reveal something that is not valid, because if we reveal some invalid nonce and number, the network would just ignore it. And again, the way the network works is very much similar to Bitcoin. So we will have specific types of messages that can get published around the network. So we will have a specific type of message that says, hey, I'm MI, here are my nonce and number, and well, everyone on the network already knows your hash. So everyone on the network would just hash these and check if they have the right hash. And if they don't have the right hash, it will not even be propagated. Okay, so you cannot reveal, you cannot lie basically about what your choice was. But one thing that you definitely can do is what's in the chat right now, and it's that you can just say, I don't reveal. Okay, so suppose that I'm again a miner who controls a large percentage of the stake. Let's say maybe I have 20% of the stake. And so if I have 20% of the stake, I probably have control of 20% of the players here. So from this M1 to MR, 20% of them belong to me as an attacker. So what I can do with that 20% is that I can just generate a bunch of random numbers, and I can announce the hashes for all of them. But then here I can wait for everyone else to reveal their nonces and their values, and then I can compute the XOR up until this point. And then I can go into all of my choices and see which choices make sense for me to reveal. So which subset of choices would give me the highest number of blocks that I can mine in the next epoch. And then I can only reveal those. And I will not reveal the other ones. Now, you might say, oh, okay, so you will just lose the fee or the reward that you were going to get for this random number generation. But yeah, I wouldn't care that much, because if I can eventually increase my share of the miners, it doesn't really matter, right? I will not get rewards for a while, but then I just increase my share over and over again, and at some point I will have a monopoly over mining, and then I can make up for all the monies that I've lost. So this is not great, and actually the property that it doesn't satisfy is the tamper-proof property. Now, one way we can kind of solve this is that we can say all the miners have to give us a huge deposit. And this is actually something that a lot of proof-of-stake protocols do. So in the proof-of-stake protocol that we talked about right now, you get the right to mine based on the total number of coins that you have on the blockchain. But instead of doing this, I can say that if you want to use a coin in mining, then you are not allowed to, at the same time, transact with that coin. So if you want to use a bunch of coins to do mining, you can create a specific type of transaction that says, I want to use these coins for mining, and then these coins will be frozen. And you cannot do any transactions with them, you cannot send them around. And then if you're chosen in this random number generation, and if you do anything fishy, if you cheat, if you don't reveal, or if you reveal the wrong number, or if you don't announce, you will basically lose your deposit. And as long as that deposit is large enough, that would incentivize everyone to take part normally and reveal, and so on. So this is how we can make our commitment scheme work for random number generation. the miners have to have something really large at stake. They have to have a really large deposit that they will lose if they don't reveal. And so the fear of losing that would overcome the utility that they can get from having a better share in the next block, and so they will not cheat. That's the way that we want to argue there. Okay, but you see that this is not great, because now we're being pushed into a situation where you either have a coin that you're using for mining and you've frozen it, or you have a free coin that you can use for everything else, but you cannot use for mining. And this is not very democratic in the sense that, well, if you're a rich person, you probably have more savings and more money that you can freeze just for mining. But if you're not a rich person, you basically cannot freeze any of your money, and so you will get no chance of becoming the miner. So it's not really as fair as we want it to be. Okay, but I want to just analyze some other properties here. So first of all, we talked about generating a random number. But what we're doing here, the protocol that we have here, is completely deterministic, right? So every player is just choosing some numbers, and then the final number is just the XOR of these numbers. So I have to be more specific, and I have to say in my protocol that every player chooses these two numbers, both the nonce and the actual number, uniformly at random. Okay. Now, as usual, when we talk about honest players, we mean players that actually follow the protocol. So if someone just uses a dummy value, for example, always uses value 0 for their xi, they're not an honest party. But here's the problem. In this protocol, you cannot really distinguish between honest parties that are actually giving you numbers that are generated uniformly at random, and dishonest parties who are just not putting any effort into creating randomness. So you can have a dishonest party that always just gives you 0 for xi, right? Because that's just the easiest thing to do. Why should I spend even the tiniest computational resource to generate a random number if I don't have to? Okay? So that's one of the problems here. The problem is that there is really no incentive to be honest in terms of generating a random number. There is incentive to be honest in terms of announcing the hash in time and revealing it correctly and so on, because we can have those deposits. But there is no incentive for randomness. But okay, let's say, forget about the incentive, let's just analyze what happens here. So a very nice property here is that even if one of the players is playing uniformly at random, even if one of the players is honest, then the final result would be a uniformly randomly chosen number, right? So suppose here I have R players, and let's say that everyone except M1 is malicious. Everyone against M1, everyone except M1 are even collaborating with each other, let's say. And they're trying to make it so that the random number becomes some specific number or makes some specific person win. As long as I have just one honest participant, as long as just M1 is honest, M1 is going to choose X1 uniformly at random. And then when I take this XOR, or actually, well, instead of XOR, I can just take the sum, right? We've seen this in one-time pad. It's the same thing. I can just take the sum modulo n, it doesn't matter. So as long as just one player is honest and gives the xi uniformly at random, this whole sum will be uniform, distributed uniformly at random. So this is a very nice guarantee. You see, we don't even need half of our participants to be honest. We just need to have one honest participant in order to get a random number here. So that's a great property. But of course, all of these worked because I added this new and extra requirement that in order to be a miner, you have to freeze some of your coins so that if you cheated, we can just confiscate those coins or burn those coins. And a very important question is, what if we don't want to do this? What if we want to go to the pure proof of stake idea that we had originally here, that your probability of getting chosen should be proportional to your stake, like to the exact number of coins that you have, not to the number of coins that you have frozen or put aside for mining. Well, in that case, this commitment scheme would not work, right? Because as we talked about before, basically an attacker can choose which parts of their, which one of their XIs they want to reveal and which ones they don't want to reveal. And that gives them some degree of freedom to increase the probability that they become miners in the next epoch. Now, I just want to finish this by talking a little bit about the homework that you've submitted about auctions. And there we have a similar case, right? The only difference there is that we're not trying to generate a random number. So at the end, we're not going to take the sum of all the numbers. Instead, we just wanted to see who wins the auction. So at the end, we would just take the maximum of all the bids. So the only difference between this and how we do auction is in step 4. Now, one question that I have asked you there, and a very common problem is that I said, how can you make sure that the highest bidder in the auction actually pays? And a lot of you had a solution that is actually wrong for a very subtle reason. And the solution was that we let people commit using the hash of their bid and some nonce, and then we make them pay when they reveal. So I've seen many smart contracts where you say when you reveal that your value is XI, your bid is XI, and your nonce is NI, you have to also pay XI. So this wouldn't work. Why? Because again, as an attacker, what I can do is that I can make a lot of different bids. So suppose that I want to buy the item and I'm willing to pay, let's say, 10 Ether to buy it. I can make different bids from 1 Ether to 10 Ether. So I make 1 Ether, 2 Ether, 3 Ether, all the way to 10 Ether. And I make these bids using different accounts, using different identities. And then when it comes the time for revelation, I just wait for everyone else to reveal. And after everyone else has revealed, I go into my bids and see what is the lowest bid that makes me win. And I only reveal that bid. So you see, even though I was willing to pay more, I was not forced to actually reveal all of my bids. So I just revealed the smallest bid that makes me the winner of the auction. So I'm just saying this so that you know that when you're designing protocols based on commitment scheme, you should be very, very careful about the timing and when people have to pay and so on. So here, for example, it's not okay if the miner has to pay a deposit only at step 3. So they have to have a deposit already before maybe even step 1, so that if they did any kind of cheating in any of the steps, we can just confiscate their deposits. Okay, so this is all for the for this session. At next session, I'm going to talk about publicly verifiable secret sharing schemes, and that's something that is probably going to take several sessions and several lectures, and we will eventually get to a point where we can actually generate randomness that satisfies all of our requirements. Oh, I just want to add one more point here, and I know we're out of time, but let me just add this. So one thing that comes to mind is that you can say, okay, if someone cheated, we will just ignore them, and we will just compute this sum without the numbers provided by the cheaters. But of course, this doesn't solve the problem because the cheater or the attacker would just then calculate whether it's better to reveal or not. So which sum becomes better for me. You can also say that if someone cheated, if they didn't announce their hash, or, well, we mostly care about this kind of cheating. If they didn't reveal, then I would just redo the whole protocol. So I can say that if I got to step 3 and someone was cheating, I say, okay, forget it. We're going to kick this person out and we're going to do the protocol again. So without this person. But that's also not going to work because, again, suppose that you are an attacker and suppose that you look at all the revelations from the other people and you see that you are actually losing the current round. You're getting random numbers that are awful for you. Maybe you're not going to be a miner in the next epoch. So what you do is that you just don't reveal. And by not revealing, you're getting another chance because everyone else is going to, again, redo this commitment scheme and generate a new random number. And so after you knew that you have not won, you could actually force a redo of the protocol. So that's also not going to solve our problem. So to capture these things, I'm going to add some more requirements here. So another requirement that I want is that I want it to have constant runtime. So I want to have a specific number. For example, I want to be able to say my whole protocol for generating randomness ends in 5 time slots. Okay? So no redos, no going back and doing it again and so on. I want to have constant runtime. And of course, I also want to have a guaranteed output. And when I say a guaranteed output, okay, I want to actually say guaranteed to output a result. Now, what do I mean by this? I mean that the protocol cannot fail. So we cannot say, oh, someone did not reveal, so the protocol just failed. We just don't have that. We have to find a protocol that always creates a random number. Why? Because, well, if the protocol fails, let's say I'm in epoch 2, and I say, oh, I failed to generate the random numbers, the protocol failed. So that's basically the death warrant for my blockchain, because now I don't have the miners for my next epoch, so my blockchain cannot go on, so the whole protocol is really useless because my blockchain has died. So we have to add these 2 extra requirements. And as you see, our security requirements are already quite a lot. And now in the next session, I will talk about ways of actually achieving all of these. Okay, so this is the end of this session. You can leave, and if you have questions, please ask in the chat. I would be happy to answer them.